So let us start with today's topic, right? We will discuss fields and lumped heat system today. Okay. So yeah, so as you know, in heat transfer, whenever we are considering convection, the rate of heat transfer from a surface at a particular temperature Ts, right, to the atmosphere, let us say it is at temperature T infinity, right, or T atmospheric. So the convective heat transfer is given by this simple formula HA delta T, right, where this delta T is Ts minus T infinity. Now here, whenever we want to increase this heat transfer, right, in that case the options with us are very limited, because this Ts and T infinity are pre-decided, right? We cannot change that. So what we can do to increase the heat transfer is we can increase this heat transfer coefficient, right? We can increase heat transfer coefficient, or we can increase the area, right, through which heat transfer is taking place. So generally this increase in H is also not convenient every time, because in case of convection, if we are dealing with this gas, then heat transfer coefficient is very less. So in order to go for high heat transfer coefficient, we need to provide some this what we can say pump or something like that. We need to provide some assistance. In natural convection, this H is very less. So the only options we are having is to increase this area, right? So for that, extended surfaces are used, right? Extended surfaces are used. So these extended surfaces are nothing but fields, right? So this is how we are having this importance of field in heat transfer. You must have seen that engine, right, or cylinder of that engine, which is surrounded by fins, right, to increase the heat transfer. Now generally these fields are made up of highly conductive materials, right? These fields are generally made up of highly conductive materials, right, like aluminum, right? So now if we consider the heat transfer in fields, if we consider heat transfer in fields, then as you can see here in the given figure, what we can do is we can assume a particular this element, right, at a distance x, right, of length this delta x. Then the heat transfer in this particular element is whatever the conductive heat transfer has entered to this element at a distance x will be converted to or transferred to the heat conduction at this x plus delta x, and the remaining will be convected, right, to atmosphere. So if we write this heat balance, so then this Q conductive at x will be equal to this heat transfer rate of conduction at x plus delta x, right, let us say delta x, plus Q convection, right. So this is how heat balance can be written in this particular case. Now as we know, this convection is given by HA delta T, where A is nothing but parameter into this particular length delta x, and here temperature difference is T minus T infinite, which is that atmospheric temperature. So if we put this value in the above equation, then we will get something like this: heat transfer rate of conduction at x plus delta x minus Q conduction at x divided by delta x plus h p plus t minus t infinite is equal to 0, right? So once you have this relation, then you can consider that this delta x is almost 0, or limit delta x tends to 0. In that case, you can rewrite the above equation at this delta q or dq conduction plus this hp t minus t infinite is equal to 0, right? So here what is this conductive heat transfer along the fin? That is also can be derived from that Fourier's law, right? What is Fourier's law of heat conduction? Can anyone tell?
Q equal to minus k dt by dx.
Right. So as we know, yeah. So from that Fourier's law of heat conduction, it can be given by this KAC dt by dx, right? So as you know, this heat conduction is nothing but KAC dt by dx, right? Now if you put this value into above equation, then you will have something like this. Correct? Now in this equation, generally fins may be of varying cross section as well as varying perimeter throughout its length, but if we consider this cross sectional area and perimeter constant, then this equation can be simplified, right? So if we consider that perimeter and the cross sectional area are constant, right, by assuming this constant, you can simplify that relation to this t square theta upon dx square minus a square theta is equal to 0, right, where a square is nothing but hp upon KAC. So this is how you are having this differential equation, right? So the roots of this differential equation can be given as this c1 e raised to ax plus c2 e raised to minus ax. Right, now here if you apply boundary condition, then you can come to the specific solution. It is general solution, right? So here at x is equal to 0, we are having that base of the fin, right? So at base of the fin at x is equal to 0, this temperature T is equal to TB. So if you put this boundary condition into that equation, then you will find this theta 0 will be equal to this TB minus T infinite, right? So at this x is equal to 0, this theta 0 is nothing but theta b, right? So this is how you will have your boundary conditions, right? Now in order to have other boundary condition, right, which is at x is equal to L, here this boundary condition is at x is equal to 0, temperature is equal to base temperature, right? Because in this fin, if you see here at x is equal to 0, this is base temperature, right? Now the other boundary condition will be at x is equal to L. So for that boundary condition, we are having 3 or 4 different cases. We will see here, right? If you see here at this x is equal to L, we can have different what you can say a boundary condition. As it is mentioned, you can have specified temperature, you can have that negligible heat loss, you can have convection, and you can have convection and radiation both, right? So specifically what we are doing is we are considering all cases one by one. So first case, if we consider very long fin, right, let us say infinite length, then what is going to happen is, at infinite length, that temperature will be of course equal to that ambient temperature, right? So that TL will be equal to T infinite, which is ambient temperature at that length, right? Very long length. So what will happen in that case is that theta L will be equal to TL minus T infinite is equal to 0, right, as this L is going to infinity. So now if you put this particular condition, then in your equation this theta x is equal to c1 e raised to ax plus c2 e raised to minus ax, only this element will take part because this will go to infinity, so this is not feasible solution. So for infinite length, your theta x will be given by only this particular element, right, c2 e raised to minus ax. Now as we have already put the initial boundary condition at x is equal to 0, and we have found that this constant is coming theta b, right? So your equation will reduce to this theta x is equal to theta b e raised to minus ax, right? Now as you know, this theta is the temperature difference, right? Theta x is temperature difference, so this Tx minus T infinite upon the Tb minus T infinite will be given as this e raised to minus x into A, we know that is Hp by Kac, right? So for a very long fin, as we know that this particular equation for this temperature difference is given by this, so heat transfer for very long fin can then be calculated by using this relation, right, dt by dx, right, at x is equal to 0. If you consider this and if you put all this value from above equation by using this at x is equal to 0, you will have this dt by dx at x is equal to 0. If you differentiate on both the sides, and you will find the value of this dt by dx x is equal to 0, and if you put it here, then you will find that it is simplified to this h p k a c, right, into this Tb minus T infinite, because here you will have this minus A e raised to minus Ax, where A is again Hp by Kac, so if you put Hp by Ka, then that under root Hp will remain as it is, and that under root Ka will be simplified as under root Ka, so this under root Hp into Kac is coming into picture, right? So I am not writing all this, but you will find heat transfer with this relation for infinitely long fin, right, and
Sir,
this temperature distribution with this one. Yes,
at x equal to L equal to 0, sir.
sorry,
Temperature gradient is 0 at infinite length.
temperature gradient is 0 at infinite length. Yes,
At x equal to L,
sorry, at x equal to L it will be 0, huh?
x equal to 0 is written.
Here we will use at x equal to 0 only in order to find the heat transfer rate for this long fin, right? For at x equal to A, you will find this dt by dx, this Tb minus T infinity will go this side, right? So this is nothing but dt, this Tx minus T infinity, right? So this is dt. So if you differentiate it, you will have this minus A e raised to minus Ax, right? And this is Tb minus T infinity at x equal to 0. So if you put x equal to 0, e raised to 0 will be 1, right? So this dt by dx at this x is equal to 0 will give you this minus A Tb minus T infinity. So if you put that value into this equation, then you will find that under root Hp by Kac minus under root hp by kac into minus kac into this tb minus t alpha, and you will get this heat transfer rate as under root hp kac into tb minus t infinity. Are you getting it?
Okay, sir.
Okay.
Mm.
Okay, so now once you have idea about this heat transfer at a very long fin, then you can have some other case also, right? So that second case is you can have insulated tape. So for insulated tape, heat transfer will be zero. This is the third case, right? So this figure is belongs to third case where convection are allowed and all, right? So the second case is this one actually, where this tape is insulated. So in that case, your d theta by dx at x is equal to L will be 0 because heat transfer will be 0, right? So in that case, this temperature distribution will be results in this one, right? Temperature distribution can be given by this relation in case of insulated tape, right? And the heat transfer in this insulated tape will be given by this minus Ka dt by dx x equal to 0. Again it will result in the same hp kac tb minus T infinite into 10 HA, right? 10 HAL, right? So this is how you are having your heat transfer in insulated tape. Now once you have idea about both this, then you need to check for the last case, that is this convection are allowed at the tip of the fin. So when conduction is allowed at the tip of fin, in that case what we are doing is we are assuming the same as insulated tape, but here what L we are using in this insulated tape it will be changed from L to L plus AC by P, this characteristic length we are going to use, right, in case of the convection at the tip, right? So if you consider any rectangular fin, right, and you calculate this LC, then it will come to L plus LT by 2, or if you go for any cylindrical fin, then you will have your LC equal to L plus D by 4, right? AC is this cross-sectional area and P is parameter. So this is how you are having your heat transfer and temperature distribution along the fin. Now apart from this heat transfer and temperature distribution in fin, you must have to have idea about fin efficiency as well as fin effectiveness. So first we will see what is fin efficiency and then we will see effectiveness. So fin efficiency means, as you can see in
Sir,
yes, yes,
please can we go to previous slide?
yes, hmm, yes,
No, thank you, sir.
okay,
Sir,
yes,
it's insulated tip, instead of the L, we place the LC,
yeah,
we get the temperature.
yeah, we are using this characteristic length. So
In second.
yeah, so we are using this characteristic length, right? So for convection we are increasing the length of insulated tip. Okay, so once you have idea about this, then we can go for this efficiency and effectiveness of fin. So basically efficiency of fin is what, as you know, you are having this base area, right? This is without fin, and if you are providing fin, then you will have this surface with fin with increased area, right? So in case of efficiency of fin, actually when you are adding fin to any surface, the ideal situation is the fin must be at the same temperature throughout, as you can see. But in actual practice it is not possible, right? Fin cannot be at the same temperature. Now why it cannot be at same temperature? Because the material must have some thermal conductivity, right? So if material has this infinite thermal conductivity, then directly whatever is temperature here can be the same throughout that solid body, but we are not having that material. So in actual practice we will have this distributed temperature along the length of fin, and because of that maximum heat transfer cannot take place. So that is why this efficiency of fin is coming into picture. So how this efficiency of fin is defined is, first you have to have idea about the maximum heat transfer rate through a fin, which is given by H into area of fin into this base temperature minus this atmospheric temperature, right? And then once you have idea about this maximum heat transfer rate, then you can define efficiency of fin as this actual heat transfer through fin upon this maximum heat transfer through fin, right? This is nothing but actual heat transfer, right? Well, this is maximum heat transfer when we are considering that the whole fin is at base temperature. So this is how efficiency of fin is defined. Now if you consider the efficiency for that long fin and all what we have considered those different cases, then if you go for that efficiency of very long fin or infinite fin, then it can be given by this Q fin upon Q fin maximum, right? So Q fin we have derived in case of this particular long fin is HPKAC TB minus T infinite, right? Now once you have maximum temperature maximum heat transfer rate, that will be given by this HA fin into TB minus T infinite, right? So if you simplify this, then this A fin can be written as this parameter into length of fin, right? A fin can be written as P into L. So if you put A fin as P into L and you simplify this, then what you are going to get is this 1 upon L under root KAC upon HP, right? So this HP upon KAC is nothing but A, which we have defined earlier, right? A square we have defined as HP by KA, so A is under root HP by KA. So this is how efficiency of long fin is given by this 1 upon AL. Now actually best book to study this topic is, I am discussing it from Yunus Senjal, so you can also check that. I have, I guess, written on the first page also. Here I guess, yeah, heat transfer a practical approach by Yunus Senjal. Okay, did you get this? Whoever has typed message. Okay, okay. So yeah, now let us go ahead. We were discussing this efficiency, right? So this is for that infinite length. Now if you go and change the case to that insulated tube, right? So in case of that insulated tube, you can have this HPKAC is TB minus T infinite 10 HA, right? That was the actual heat transfer, and here HA fin upon TB minus T infinite will remain same. So basically it will remain same. What is going to happen is this will be multiplied with this 10 HAL, right, where A is under root HP by KA. Right, now for the third case, just you need to replace L with LC, right, for the third case. Okay, in which convective tip is there, right? You can have convection at the end of tip. So this is how you are having efficiency in your fin, right? Now after efficiency, you must also have idea about the effectiveness of fin, right? So effectiveness means what change or what how effectively the fin is increasing the heat transfer. That is basically effectiveness of this fin, right? So this effectiveness of fin is actually defined as this Q with fin and Q without fin, right, when no fin is provided. So basically this ratio must be greater than 1. Then only,
Sir,
yeah,
can you go back to the previous slide, sir? I had a power cut.
sorry, yeah,
Can you go back to the previous?
yes,
Uh, okay, sir. Thanks.
okay. So yeah, here effectiveness of fin is, as we have already defined, that the heat transfer must be increased after the addition of fin, then only this is justified, right? So effectiveness of fin is how the heat transfer rate is increased, so it must be greater than 1, right? So heat effectiveness of fin is defined as heat transfer with fin divided by heat transfer without fin, right, or in absence of fin. So if you write here, then this actual fin or the heat transfer through actual fin is also given or defined by this efficiency of fin into that maximum heat transfer through fin, which we have written just now, right? This way it can be represented, actual heat transfer through fin with the help of this efficiency and maximum heat transfer. It can be defined like this, while Q without fin can be simply written as HAB, only base area will be there, right? This way you can define your efficiency of fin. So basically this area of fin divided by base area into this efficiency of fin. This will define the effectiveness of fin. Here also you can write for those different keys, right? Let us write for that long fin or infinite long fin how effectiveness will be calculated. So for long fin you can write this HPKA and here you will have HP, and as we know, almost this base area is almost equal to that cross section area of the fin. So for that you can come up with simplification like this KP upon HPC. So this is how effectiveness in long fin is defined. So these are some of the important things which is related to the fin, temperature distribution in fin, then heat transfer rate in fin, effectiveness of fin, and this efficiency of fin, right? Now one more important thing is length of fin needs to be defined. Now how you are going to define the length of fin is actually after certain point of time there is no heat transfer through fin. Why? Because at a certain length of the fin the temperature already reaches the temperature of this ambience, right? So as we have seen in that particular efficiency slide, if you have observed, we have shown the ideal case or actual case, right, where this particular temperature is decreasing throughout the length or across the length of the fin. So why it is always important to decide the length of fin or optimized length of fin or proper length of fin is if you go on increasing this length, then at certain point of time, if you are considering ambience temperature is 25 degrees centigrade, then this fin itself may reaches the temperature of this 25 degrees centigrade. Now after that point, if you keep on increasing the fin length, then it is not going to take part in any heat transfer. It is obvious, right? Yes or no?
Yes, sir.
Okay, so that is why it is always advisable to define this length of fin. So here what one example they have considered, right, and how they have come up with this calculation is they have considered the heat transfer ratio, right. Let me define that heat transfer ratio. So this heat transfer ratio is nothing but this heat transfer through fin divided by that heat transfer through that long fin, right. So if you write that actual heat transfer through fin as we have calculated for that short tip with convection at end with this relation, right, and the long fin or infinite fin is having this HPPAC minus T infinite. So this will give you this 10 HAL itself. So that is why they have considered this particular factor 10 HAL, right?
LC,
Sorry?
for insulated tip ends.
Sorry?
LC, sir, can hyperbolic of ALC.
10 hyperbolic of AL.
LC, characteristic L.
Here, here in case of this what we can say, that short fin, it must be that characteristic length as we have decided. Yes, correct. That is what you were asking, right?
Yes, sir.
Okay, yes. But basically it is this 10 hyperbolic of AL, right? So if you keep on increasing the length, then what is going to happen is, as you can observe, at this AL of 5 you are getting this value 10H AL as 1. It means both what we can say case are giving the same result, means that finite length is equal to infinite length at this AL is equal to 5. It means after this point there is no point of increasing the length of fin. Apart from this, one more observation you can make here in this given example is, if you see at this 2.5 this AL, or that at that particular length, this is almost 99%, right, 0.987. It is almost 99%, and here it is 100%, right. So from here to here only 1% change in heat transfer rate is there, right. So in order to get 1 more percent of heat transfer rate, your material gets doubled, right, if you are using that doubled length. So in that case we can also take this as length instead of this, right. So this is how length of fin is decided. So are you getting what are we discussing? Okay.
Yes, sir.
Sir,
Okay.
up to here we are putting it.
Sorry?
Miss, can you repeat that point up to which we are fixing?
We are fixing at this 2.5, right, because from 2.5 to 5 there is only 1% increase in heat transfer rate, while our material will be doubled because the length will be almost double from reaching this 2.5 to 5, right. We are using this certain length of this fin, right. So at 2.5 we are having 99% of heat transfer, right, and for this remaining 2.5 other that 1% of heat transfer is there. So we can sacrifice this 1% of heat transfer rate in order to save the material. Are you getting?
Yes, sir.
Okay. So now, apart from fin, one more thing we are going to discuss, that is this lumped heat systems, right? Lumped heat systems means while this heat transfer, right? Generally, we are considering uh, what we can say contours of heat transfer, right? Means it also changes with location, right? Or spatially it is going to change, right? And the other is that transient means with respect to time it is going to change, right? So with respect to location and with respect to time, heat is going to change. So what happens is, in some examples you can have what happens is, in some examples you can have the same temperature throughout the what you can say body of your object, right? Suppose if you consider a particular ball, let us say, made up of material which is having this conductivity K1, right? If you are taking it out from a microwave oven, then it will be at certain temperature, right? Now this K1 is so high that the all temperature is almost same, right, throughout the body, right? While in other case the conductivity of material is K2 and you are having the same dimension ball of that material with conductivity K2, which is having actually contours of temperature. It is not having same temperature throughout the body when you are taking it out from oven, because the heat has not conducted throughout the body at this instant when it is supplied to the body. Actually, in oven heat is supplied to this body right through the surroundings, right? So it is this is how if the conductivity is too high, then the full body will be at same temperature after certain point of time, while in some of the material it is not possible. So in the material where the body is at the same temperature throughout, for that we can go for this lump heat analysis, right? Or those are called as lumped systems. We will also see how we can identify whether the system is lumped system or not, right? So actually for that what you need to do is you need to first what you can say you need to first check the Biot number in order to check whether the system is lumped system or not. So Biot number is nothing but convection at the surface divided by this conduction within the body. Right. So basically, if you write this both, then you can come up with this HLC by K, where this LC is characteristic length, which can be calculated by volume upon the surface area. Right. So here this convection H A delta T, and here it is K delta T dt by dx. This is simplified to this HLC by K. Right, so this is known as Biot number, and here it is written in terms of convection and conduction. If you go and write it in terms of conduction resistance and convection resistance, then it will be reversed, right? Because conduction resistance is LC by K and convective resistance is 1 upon H. So it can also be written in terms of conductive resistance and convective resistance. So basically this Biot number says how conductive your material is, how predominant conduction is, right? So if your conduction is very much high or very predominant, then it will almost goes to infinity, as we have seen in that fin, that if the fin is at the same base temperature throughout, right, then it will give the highest efficiency. For that we need that K to infinity. So here also, if your conduction is almost up to infinite, then what will happen is this Biot number will tend to 0. In that case, this lumped system will give the perfect result, right? But if Biot number is less than or equal to 0.1, in that case also you can have some approximate result, and you can have some accuracy with which you can predict your heat transfer. So when you consider this lumped system, you need to consider only the change with respect to time, and you need not to see with location or with position the temperature difference is there in existence or not, because we are considering that it will be same throughout, right? So when Biot number is this less than or equal to 0.1, you can go for this lumped analysis, right? So when you go for this lumped system analysis, actually when you go for this lumped system analysis, then what happens is heat is transferred into the body, right, during the time dt, as we have seen that example that providing heat through oven, right? So heat transfers into the body, right, during the time dt, and due to that the increase in energy of the body, right, during the same time, there is increase in the energy of the body, right, during dt. So if you provide further simplification, then it is nothing but h is t infinite minus t dt equals mcp dt, right? So here this dt is related to the time, this dt is related to the temperature difference, right? Here you can further simplify by putting this m as this rho into v, and your dt is nothing but t minus t infinite. So if you do this changes, right, and if you further write the given equation, right, you can rearrange it by putting this value into above equation. How you can rearrange it is like this: t minus t infinity Nusselt number also the same way. How Biot number is different from Nusselt's number? Actually, Nusselt number and all are related to that. What you can say? Hello.
Nusselt number related to the fluids.
Yeah.
K here Ks means thermal conductivity of the solid.
Yes. Correct. Okay. So here this this d we can rearrange it with this dt minus t infinite upon this t minus t infinite, right, equals minus h a s upon rho v cp. Here this negative sign has come because we change this t infinity minus t to t minus t infinity here, right? So this is how you can have now after simplification you can give it like this, and then you can integrate it from that temperature at initial position at Ti and at particular time t. So if you integrate it with that limits, then you will find like this. You can have this relation right? So now if you further simplify it and write it in terms of temperature difference at a particular point of time, that is dt, which you may be interested in, so you can calculate it with this relation now, right? Sorry, here it will be. So this HAS upon rho VCP can be considered as a time constant, right? You can write this HAS upon rho VCP with an constant B, which is nothing but time constant. So it can be written as this Q minus BT. Okay, so this is how you are having these two different analysis, right, in terms of temperature distribution and heat transfer rate and all, in case of your lumped system analysis and this heat transfer through fins and all this we have seen, right? So generally this is important from that gate point of view. They may ask some questions regarding that. We will see some of the questions asked in previous gate question papers.
Sir,
Yeah.
in that previous formula, the time constant is rho Vc by Ha or Ha upon rho Vc.
HA upon rho VCP.
Then there will be means e raised to time constant has units or not?
That I need to check. You can check actually.
No, because means e raised to something unit quantity. I thought e raised to the for e to the power something, that something should not have any units.
That I also need to check whether it has any unit or not. You can check, but I guess how you can check that. You can put units of each and every thing, right? What is the unit of H?
Watt per meter square per kg.
Let us check, right? 1 second. Here. Yeah. Watt per meter square Kelvin. What is area meter square? Huh? Then what is rho?
Kg per meter cube.
Yeah. And volume meter cube. What is CP?
Kilojoule per kg Kelvin.
Or joule per kg Kelvin, kilojoule per kg Kelvin, whatever. So meter cube can be cancelled, this can be cancelled. Here this Kelvin can be cancelled, kg. Yeah, so it is, I guess, unitless, right? This watt and joule are also works unit, correct? Yes or no?
No, but watt is joule per second.
Sorry?
Watt is joule per second.
What is per unit time, huh?
Yes, sir. 1 by S.
Okay, then here this t will be then going to be cancelled. That second will remain, whatever is remaining here, right? Correct. That what will be joule per second. Here it is kilojoule. So that second will be then cancelled to this second. Yes or no? Correct?
Yes, sir. Means time constant has unit per second.
Yeah. Correct.
Okay, sir.
Okay. So is it clear now? Clear, yes?
But it's clear, sir. But as the name suggests, time constant, so I thought it should be also in second.
It should be?
Also in second.
Okay, but here it is second inverse, huh? That is why you are telling the times constant is rho VCP upon HS. You are telling like that, huh?
Yes, sir.
Okay. Maybe then you will be correct. I will check. Okay.
Okay, sir.
Okay, now let us go to this previous year questions. So it is from GATE 2004 that a spherical thermocouple junction of diameter 0.706 mm is to be used for the measurement of temperature of a gas stream. The convective heat transfer coefficient on the bead surface is 400 watt per meter square Kelvin. Thermophysical properties of thermocouple material are this K is equal to 20 watt per meter Kelvin. This Cp is given as 400 joule per kgK and rho is 8500 kg per meter cube. With thermocouple initially is at 30 degree centigrade is placed in a hot stream of 300 degree centigrade, then the time taken by the bee to reach 298 degree centigrade. Can you try this question?
Yes, yes, sir.
Yeah, please try this. I guess you will be able to solve this. First, you need to check whether lumped analysis is possible or not. Yes? So what is given here is this heat transfer coefficient is given as 400 watt per meter square Kelvin. Then this thermal conductivity this is 400 joule per kg. Kg per meter cube, right? Then you have to find the time, right, where it reaches 298 degree centigrade. But before that, you need to calculate this Biot number, that is HLC by K. You have H and K, you need to calculate LC, which is V by AS, right? Volume by surface area. So what is the volume? Here volume will be pi by 6 TQ, right? And the surface area is something like pi d square. So with this, your characteristic length will be d by 6. D is given as 0.706. So you will have 0.706 by 6. Point 0023 is Biot number, correct. So your characteristic length is 0.706 by 6 into 10 raised to minus 3 meter. So if you put all this value into this Biot number, then H is 400, LC is 0.706 by 6 into 10 raised to minus 3, and K is 20. So it is coming 0.0023. All of you are getting this? All of you are getting
Lumped
this?
system. Yes, sir.
Yes.
Yeah, so it is lumped system. So now
Yes.
you can go for that time calculation. So for that you can use the temperature distribution equation which we have derived just now. This Tt minus T infinity Ti minus T infinity is equal to E raised to minus HAS upon rho Cp into T. Correct?
Yes, sir.
So here you are having all the data with you, right? This temperature is given as 298, this is 300, this 30, this 300, e raised to minus, H is 400, then V by AC directly you can write, right, that 0.706 by 6 into 10 raised to minus 3, and then rho is given as 8500, and here the CP is also given as 400. Into T, correct? So this will give you T. So can anyone tell what is the answer?
Sir, what is CP?
CP is this 400. So what is T? Can anyone tell the answer?
4.0.
4.9.
Sorry?
4.9.
4.9 second is the answer, right? So it must be given in option, I guess. So this is the correct answer. Okay. So now if we go to the next one, here a small copper ball of 5 mm diameter at 500 Kelvin is dropped into the oil bath whose temperature is 300 Kelvin. The thermal conductivity of copper is 400 watt per meter Kelvin. Its density is 9000 kg per meter cube, and its specific heat is 285 joule per kg cube. The heat transfer coefficient is 250 watt per meter square Kelvin, and lumped analysis is assumed to be valid. The rate of fall of temperature of the ball at the beginning of cooling region. Here you are already told that lumped analysis is there. So you need to now give this rate of fall of temperature at the beginning. Means at T is equal to 0 you need to define all this. But for that first you need to write that. Please mute yourself. Some of you are not muted. Hello. Please mute yourself. Yeah, so first you can use this equation, right? And what you have to do is you have to write it in terms of this differential equation, right? dt by dt, which can be actually written, sorry, first you can write one more step for your simplification, that this dt is nothing but this t infinite plus ti minus t infinite e raised to minus this h is on rho t. Now if you differentiate it with respect to t, then this dt by dt can be written as this minus h upon rho is cp into this t minus t, because it will go to 0, it is constant t infinity, right? It's 2hs upon rho cp into t, right? So this is how you will get your rate of change of temperature with respect to time. Now what you are asked is, you are asked to find it at t is equal to 0. So at t is equal to 0, if you put t is equal to 0, e raised to 0 will go to 1, and you will find this dt by dt at t is equal to 0 as directly this h a, only magnitude if you are calculating, then it is h a upon rho v c p t a minus t infinite. You are having everything with you, I guess. So now you can calculate. Can you calculate this? Hello?
Yes.
Yes, sir.
Please calculate.
Sir, please
Yeah,
show the data.
Data, yeah. You can have the data. If you write data, K is given as 400 watt per meter Kelvin. Then Ti is 500 Kelvin. Rho is 9000 kg per meter cube. And this T infinite is 300 Kelvin. The Cp is 385 joule per kg Kelvin, and H is also given as 250 watt per meter square Kelvin. Now if you put all these values, H is given as 250. V by A can be here also D by 6, right? So D is given as 0.005. So V by A I will write as 0.005 divided by 6, right? And here rho is given as 9000.
Sir, is it 17.316?
2.316.
Yes, correct. So this is how, if you put all these values, then you will find it as 17.316 Kelvin per second at t is equal to 0. So this is how you can get this rate of change. The next is the average heat transfer coefficient on a thin hot vertical plate suspended in steel air can be determined from observations of the change in plate temperature with time as it cools. Assume the plate temperature to be uniform at any instant of time, and the radiation heat exchange with the surroundings is negligible. The ambient temperature is 25 degrees centigrade. The plate has a total surface area of 0.1 meter square and a mass of 4 kg. The specific heat of the plate material is 2.5 kJ per kg. The convective heat transfer coefficient in watt per meter square Kelvin at the instant when the plate temperature is 225 degrees centigrade, and the change in plate temperature with time dt by dt is minus 0.02 Kelvin per second is. So can you try it by yourself?
Sir, means by we here also the same equation, and we have to find H.
Yeah, but yes, you can go by that, but here I guess you can better go with that simple equation with which we have started, right? That at heat transfer, that convective heat transfer to the system will be HAT minus TF, right? And heat added to the system as MCP
Equal to MCP.
dt by
Yeah,
dt,
MCP dt by dt.
right? Here actually it
Yes.
is rate, so here dt was there, right, in our that equilibrium, right? So this dt I have
Yes.
shifted to here, so you can try with this. Okay.
0.01 or
I guess you have not converted that 2.5 kilojoule per kg. Because H into area is 0.1 meter square into T minus TF is 225 minus 25. M is 4 kg. Here it is 2.5 into 1000, right? Kilojoule per kg. And dt by dt is minus 0.02. Correct?
yes, sir.
So from this you will get H. So what is H?
10, sir.
10.
10 volt per meter square Kelvin. So this is your answer. Okay, now next let's see. A fin has 5 mm diameter and 100 mm length. The thermal conductivity of fin material is 400 volt per meter square Kelvin. One end of the fin is maintained at 130 degrees centigrade and its remaining surface is exposed to ambient air at 30 degrees centigrade. If the convective heat transfer coefficient is 40 volt per meter square Kelvin, then the heat loss invoked from the fin is. Can you try this one?
Under the case 3.
Yes, here D is given as 0.005 meter, right? 5 mm is 0.005 meter. Then area you can calculate is pi by 4 d square. So if you calculate, what will it be? Area, can anyone tell? (1.96 into 10 raised to minus 5). All of you are getting this meter square.
Sir, here which area means outer area or
The cross-sectional area, cross-sectional area. This fin will be like this, na? Cross-sectional area, right? Are you getting?
yes, sir.
Yeah. So length of fin is 100 mm, right? It means 0.1 meter. That A value you can calculate, right? HP by KAC. Because you have H and K with you, perimeter is nothing but pi d. So H is given as 40, right? Heat transfer coefficient. And here conductivity K is given as 400. So it is 40 by 400 into pi d. D is 0.005. Right? And this A you have calculated 1.95 or 96 into 10 raised to minus 5. So this will be what? 8.97
Yes, sir.
meter inverse, right? Now A into L will be what? 0.897, right? Because L is 0.1. So if you multiply this A and L, then you will have 0.897. Now this fin is with insulated tip we need to consider, right? Because for long fill there is a condition that this AL must be greater than this 2.64. This we have seen over there, right? This AL was coming the 2.5 and all, if you remember, right?
Yes, means E greater than
Yeah,
5.
here it is
Yeah.
insulated tip. So for that this heat transfer is given by HPKAC, this T naught minus T ln 10 HAL, right? 10 HAL. So you can have all the values with you. T naught is base temperature, basically this TB, that is given as 130 degrees centigrade. Ambient temperature is 30 degrees centigrade. So you have everything with you. So can you tell me what will be your answer?
Sir, AL greater than the 2.64.
Sorry?
AL greater than the 2.64.
Huh?
How we
So
conclude?
this we have seen, that length of fin here. So at some 2.6 or something, it may be exactly 0.99 or something, right? Here it is 0.987, here it is 0.995. So for only 1%, we are not wasting more material. Are you getting?
Okay, sir.
Going for infinite length.
Okay.
Yeah, so tell me what is your answer here? Anyone? Yes. You have everything, right? H is equal to 40, perimeter is pi d, K is given as 400, area you have calculated that 1.95 into 10 raised to minus 5. This is 130, this is 30, AL you have calculated 0.897. So tell me the answer. Anyone?
So would it be 5?
Yeah, it is almost 5 volt, right? So your answer will be 5 volt. And this is given here. So the next is a spherical steel ball of 12 mm diameter is initially at 1000 Kelvin. It is slowly cooled in a surrounding of 300 Kelvin. The heat transfer coefficient between the steel ball and the surrounding is 5. For the thermal conductivity is this 20. The temperature difference between the center and the surface of the steel ball is. Can you calculate this one? Actually here you need to first understand the question and then you can attempt this one. So what do you think? Can anyone tell me how can we approach this question?
So first should we calculate the Biot number?
Yes, correct. You should calculate Biot number in order to get idea that which resistance is higher and
Resistance is higher.
yeah, which resistance is higher, that will be understood from Biot number. So calculate that Biot number. What is Biot number?
HL by K.
Yeah, you will have H LC by K. What is LC? Volume upon surface
Have to calculate.
area, right? Volume upon surface area, right?
Mm-hmm.
So here it is spherical steel ball, so it will be d by 6, right? Pi by 6 d cube upon pi d square. So h by k will be as it is, pi by 6 d cube upon pi d square. So that is d by 6. So it is h
2 mm, sir.
k into 6. Sorry?
L 2 mm.
L. What is d? Yeah, 2 mm.
D is
yeah,
2
yeah,
2
correct.
mm.
2 mm. Yeah. Correct. So h is, but you need to convert it into meters, right? h is given as 5, k is 20,
0.5 sir byte
2
number.
into 10 raised to minus 3, 2 into 10 raised to minus 3, right?
Oh,
Right? So it is
yes sir.
0.5 into 10 raised to minus 3, it means 0.0005. Yes or no?
Yes sir. Yes sir.
So what does it mean now?
Lumped parameters.
Sorry?
Lumped analysis we may apply.
No, but what is the question here? Check the answers. What are the options? Which option you think is correct? What they are asking is
Sir,
the
D.
temperature difference between the center and the surface of the steel ball, as we have considered, right, in or while discussing that lumped parameter. It will almost be same, as lumped parameter is applicable at center and at surface. Temperature will almost be same. Here also it may be the T naught, here
D
also it
D
may be T naught.
D
So
sir.
yeah, the difference is small because conduction resistance is far less than the convective resistance. Okay,
Mhm.
right, now let us go to the next one. Which one of the following configuration has the highest fin effectiveness? Yeah, can you try?
Thin and closely spaced fins.
Yes,
Sorry,
sir.
sorry.
A sir.
Thin and closely spaced fins.
Why? Correct. That is correct. Why?
Because thin will give higher surface area, and by placing them closely, we can arrange more pins.
Yeah, actually, you can uh, provide it in terms of some mathematical form also, right? As we have discussed that effectiveness is nothing but heat transfer with fin and without fin, right? With fin and without fin. And for that, if you further simplify, then you will come to know, we have considered, right, one for long fin it is kp upon has, right? So here actually this effectiveness is proportional to this under root of, inversely proportional to the under root of this area, right? So if you are going to provide this thin and closely spaced fin, then in that case you will have that highest effectiveness, right? Is it okay?
Yes sir.
Okay. So for lower value of cross-sectional area, it must be thin, right? Then only effectiveness can be higher.
Widely spaced pins, sir.
So in case of that widely spaced, you may not have that perimeter, which is also important thing, right? Here perimeter is also important thing. So if you widely going to space it, then total surface area available in this perimeter will be less. So that is why widely spaced is not correct. Okay, are you getting?
Yes, sir.
Because if you
Sir,
widely space your fin, then perimeter area available for heat transfer, that surface area will be less, right? Though it is thin. Are you getting or not?
but if
Huh? Yeah,
but if it is thick and closely spaced, then due to thick fin, we will have more perimeter.
no. Thick means that area will be higher, right? In case of thick, if you consider this as a fin, right, and this as fin, right, in place of this, right, are you getting? So perimeter is only this much, right, in this case, while here perimeter is this much, all this surface area is going to be considered. Are you getting? Perimeter will be
Yes,
much
sir.
more in case of this thin in consideration with this thick, right? Are you getting?
Yes, sir.
So
Yes,
that is
sir.
why thin and closely spaced pen is correct. Are you getting it?
Yes, sir.